Hi, today we're going to continue moving right on through the information. Just to reactivate what we were thinking about before, when you take a minute, table M, just put it right above my head, evaluate this student's claim. Are they right? Are they wrong? Based on the methyl orange information, the pH should be greater than 4.4. If the litmus is red, less than 4.5. It should be somewhere between 4.4 and 4.5. I would say 4.45 would be a wonderful guess as to the pH. That's some very, very specific information to get. I wanted to play a video, make any observations that we can make.
Neutralization reaction. How to treat a bee sting. Hey, hold on. Don't go near that honeycomb. Please listen to me. It is quite dangerous. Fine, go ahead. See? I told you. Okay, now don't worry. Put this baking soda solution on the bee stung area. You got some relief, right? Do you know why you got relief? This happened because a neutralization reaction took place when we applied baking soda on the stung area. The venom of a honeybee contains formic acid. When it stings us, it injects that acid into our skin. Formic acid causes immense pain and irritation. However, when we apply baking soda solution, which is a mild base, on the stung area, it neutralizes the formic acid and cancels its effect. As a result, the sensation of pain and irritation decreases and we get some relief. Such a reaction between an acid and a base is called neutralization. In neutralization, both acidic and basic solutions neutralize the effect of each other, and the nature of both acids and bases gets destroyed. Hey, wait. What are you doing? Don't tease that insect. It is not a honeybee. It looks similar to a honeybee, but it is a bit longer. It is called a wasp. At least this time, listen to me. Okay,
but
don't listen and bear the consequences. Applying the baking soda is not going to help. See? Nothing is happening. I will tell you what to do. Pour this vinegar on the stung area. You will get some relief. Why do you think the baking soda solution did not help in this case? Earlier, in case of the honeybee, we learned that its venom is acidic. Hence, baking soda, being a basic solution, helped to neutralize the effect. Now, in case of a wasp, the nature of its venom is basic. When it stings us, it injects the venom into our skin. The venom causes us pain and itching. Now, baking soda is also a basic solution. Hence, it will not provide any sort of relief. However, when we pour vinegar, which is a mild acid, on the stung area, the acid, that is, vinegar, and the base, that is, the wasp's venom, get neutralized. As a result, the sensation of pain and itching decreases and we feel better.
I think we've got a lot of information here to work with. In the past, I've shown a different video. I used to show a scene from the movie Fight Club, but I think we're gonna skip that today. The problem is the scene, like that's the operative part of the scene, but there's a lot more dialogue and exposition going on. Fine, I'll show just enough to not get the copyright box annoyed.
This is a chemical burn.
To understand really what's going on with neutralization, I wanted to first get a bit of a perspective as to why neutralization does what it does. Take for example, a sample student spills a 10 milliliter sample of 1 molar hydrochloric acid. So just to make sure we're all on the same page, to find the pH, that would be the negative log of the H plus concentration. Since this is an acid, the H plus concentration is equal to the HCl concentration because it dissociates when it dissolves into water. So that's the negative log of 1, which is in fact equal to 0. To clean up the spill, if the student were to pour water onto it, this would cause what we call a dilution to take place, where now our total volume is 1 liter. So we have a 10 milliliter sample of 1 molar. This is, if you do some quick math, 0.010 moles. As we pour 990 milliliters of water into the 10 milliliters, we're now going to divide that by 1 liter. And so we have 0.010 molar. So the new pH would be negative log of 0.010, which is equal to 2. So taking a 10 milliliter sample, which is, a very small amount, and diluting it down to a whole liter, only changed the pH by a factor of 2. For me, that kind of sounds like why this is ineffective. The pH doesn't change quickly enough. And that's true of any acid or any base. If you have an acid or a base and you try diluting it, the volume of water needed to get to a point where you would consider it neutral, 7, as a pH value is astronomically large. And so instead, this is where a neutralization would take place. So just to really put a cap on it, if you take H plus aqueous and you add water to it, your products will be H plus aqueous and water. No chemistry takes place. This is largely why the use of water doesn't actually change much about the acid spill. Yeah, you spread out the H plus ions, but they are still H plus ions and they're still capable of doing what acids do. Instead, if we were to take these H plus ions and react them with something, say hydroxide ions, the product would then be water. Now, what's beneficial about this process is now we've taken an acid as a substance and we turned it into something that is neither acid nor base, it is neutral. Up on the top, if we were to take the acid and add water to it, we haven't actually changed the chemical structure. So that's where this neutralization process gets its definition. Chemical reaction between acid and base to create water. And it is true that if you had an acid and you added a basic solution to it, you would actually create water molecules. You'd make all these water molecules. Yes, there's probably still a little bit of acid or a little bit of base left over, but if you're careful with your mixing, that process, what you end up with is something that's so close to neutral at the very least so that it's not going to be dangerous anymore. So as a specific example, let's pick two substances we're very familiar with. We've used a lot. So hydrochloric acid and sodium hydroxide. In going through this reaction, two compounds reacting, so this should be a double replacement reaction. One of our products is going to be water, and that's when the OH from the base and the H from the acid, the OH minus, the H plus come together, HOH, H2O. And then the other product that is left over is you should get sodium chloride aqueous. So in our specific example, we have an acid, hydrochloric acid reacting with sodium hydroxide to make water plus sodium chloride. If we were to take that into a general form, just what substances are present are represented by each specific chemical. Acid and base will react to yield water and salt. The neutralization reaction always creates salt. That being the other process. So yes, if you were to perfectly chemically neutralize hydrochloric acid and sodium hydroxide, you would create salt water, which is fine to drink, even though it's probably not super palatable. And that's okay. But technically, if you look at that general form, we learned a long time ago that salt doesn't specifically refer to sodium chloride. Salt refers to any ionic compound, which means in the general form, any acid reacting with any base will create a salt and water. So to let you guys get some practice with this, here are 3 different neutralization reactions. I want you to pause the video. It's written all here. I want you to complete these chemical reactions to create the products. You do need to balance them. So go ahead and do that now. Excellent. Welcome back. So first, lithium hydroxide and hydrofluoric acid. Don't worry about the names. It's okay. This one's not in your reference table, and that's fine. But again, we're going to react the H and the OH to make H2O, and what's left behind is going to be LiF, lithium fluoride, aqueous. This one looks balanced to me, so we're going to move on. Now for this, we've got H and we've got OH, but now we've got some 2's to play with. So keep in mind that when we have a salt, those are H pluses and these are OH minuses. This 2 means that there are 2 OH minuses. This 2 means that there's 2 HBr's and then by extension, 2 H's. So we really are going to react 2 H pluses and 2 OH minuses to make 2 waters. And then you also have to keep in mind that these substances, remember that an acid is in water, behaves as an ionic compound. So this is a Br minus and this is a calcium, but calciums are in group 2, so they're 2 pluses. So when we swap the cations in our double replacement reaction, we have Ca2 plus and Br minus. We swap our charges and we get CaBr2 aqueous, calcium bromide. So taking a look at that just to check really quickly, I think we're balanced. Yeah, we're balanced. And then finally, we've got, again, 2 H pluses. We've got 2 OH minuses. Remember that the polyatomic ions don't split any further. That's going to be kind of important. So again, we're going to make 2 waters. And this is sulfate, so that's SO4 2 minus from table E. And this is potassium, K plus, found in group 1. So when you take those and you swap them, you should get K2SO4 potassium sulfate, and that's balanced 2. Just as a quick reminder, don't forget in a chemical reaction, you don't just take the subscripts. You have to unswap, trade the ions, reswap. Now that being said, if a salt is always the product of a neutralization reaction, you can kind of work that in reverse. You can kind of ask, well, if I know I make lithium fluoride, remember Li plus, F minus, 1-to-1 ratio, what acid and what base would react to make lithium fluoride? This is relatively easy to do as long as you remember what is true about H plus and OH minus. Most bases are metal hydroxides, so what metal hydroxide contains lithium? This is easy enough to do. If you split these back, you unswap them, you get Li plus and F minus. Well, Li plus would have to pair with the hydroxide ion to make a neutral compound. So LiOH would be a substance, a reactant. We're kind of taking our products and unreacting them to see what reactants would make them. And then the F minus would have to pair up with a positive ion, and that's H plus. We swap them and we get HF. So in this way, you can kind of undo a neutralization to figure out what acid and base would have reacted to make this salt. And that process is called hydrolysis, literally splitting water, because since we're kind of undoing the chemical reaction, we're taking a water and making an OH minus and an H plus. And just to check, did we get it right? This is lithium fluoride, HF, LiOH, hydrofluoric acid, lithium hydroxide. That's it. Try and figure out what acid and what base would have reacted to make those 2 ionic compounds. Excellent. Iron 3 nitrate. We need to figure out what our charges are. Remember, the 3 means iron plus 3. Nitrate means, or is NO3 from table E. It's got a -1 charge. So in pairing these up with hydroxides and hydroniums, or hydrogens, to make sure that we make a neutral compound, what we should get is iron 3 hydroxide and nitric acid. And that's found on table K. Don't worry about naming them. I think if we can get the chemical structure, we'd be good. Keep in mind that this is definitely not what I would call a balanced reaction because I didn't actually complete it. But yes, I think the nitric acid would be in a 3-to-1 ratio with the iron 3 hydroxide. Barium carbonate, doing the same process, your two substances should be barium hydroxide, BaOH taken twice, and carbonic acid, H2CO3. That's about the ins and outs of neutralization and hydrolysis. So in summary, acid plus base will always yield salt plus water. This chemically neutralizes both acid and base. And I didn't mention that. If you have an acid spill, you want to grab a base. If you have a base spill, you want to grab an acid. Way better than dilution and hydrolysis is the opposite, where you get an acid and base with salt and water. Now, just as a final note, the hydrolysis reaction is not always one that, well, it gets into some weird territory because you don't mix salt and water and get an acid and base. There's a really good reason why, but let's not get too far ahead of us. Let's just leave it at this. You can hypothetically figure out what acid and what base would have made a salt by looking at a hydrolysis reaction. Thanks for watching.